The next theorem is called the first isomorphism theorem. Okay, first we have two groups, G and H, and we have an epimorphism, F. Okay, so this is not just a homomorphism, it's epimorphism. It's a surjective homomorphism. Okay, and suppose the kernel of F is K. Okay, and then, so as we have seen before, we can define the quotient group G over K, which is an epimorphism. Let's call this G. Then there is a isomorphism from G over K to H. Okay, so there exists an isomorphism. Let's call it H. Okay, so this. So if there is, so what's given is this F, okay, which is an isomorphism. Then there exists this isomorphism, okay, where K is the kernel of F. So let's prove this, and somehow we need to construct this isomorphism H. Okay, first let's define this as uh, the following. First of all, for each element of G, we have f of A, which is an element of H. And every element of G over K, so the quotient group of G by K, is a coset of this form. Okay, so we want to define this mapping H. This maps to, let's say, f of A. Then we may be able to define this function, this mapping H. Okay, so for every coset of this form, Ka, then we map this element to this element of H. Okay, so first thing we need to check is that this is well defined, because this mapping H is defined on the set of cosets. We need to show that this the result of this mapping does not depend on the choice of the representative element of the coset. Okay, so that means if Ka is equal to Ka prime, then we need to show that H of Ka is equal to H of Ka prime. Okay, so let's try to show that. So okay, if this is true, then there exists some element of K such that A prime is equal to Ka. Okay, so let's see. So that means f of okay, so H Ka prime is f A prime, but that is a f of Ka because of this. But f is a homomorphism, so this is fk and fa. But k, this k is an element of the kernel of f, okay, by definition, this is a kernel of f. So that means f of k is equal to the identity element of h, which is equal to f of a, which is equal to h of k a. So therefore, the result of this mapping h does not depend on the choice of the representative element of the coset. Therefore, h is well defined. Next, we show that this mapping h is surjective. Okay, so we need to show h is surjective. In fact, for every element C in H, there exists an element of G such that f of A is equal to C, because since f is epi. Okay, so epimorphism means it is a surjective. It is a surjective homomorphism. So for every element in H, there is some element in G such that f of A is equal to C. So this is okay. But this means so there exists this A, so based on this A, we can so therefore there exists a coset Ka in G over K, such that therefore there exists a coset Ka in the quotient group G over K, such that HKA is equal to f of A, which is equal to C. So every element in H has a corresponding coset in G over K. Therefore, H is a surjection. Okay, so we already said that. Therefore, H is a surjection. And next, we show that H is injective. In fact, if H of Ka is equal to H of Kb, then by definition, f of A is equal to f of B. Okay, because this is equal to this, and this is equal to this, by definition of H. And so by multiplying by the inverse of f of B, then we have FA FB inverse equal to EH. But F is a homomorphism, so this means FA FB inverse is equal to EH. And again, F is a homomorphism, so f of A B inverse is EH. Therefore, AB inverse belongs to the kernel of F. But this means this is equivalent to Ka, the coset Ka is equal to the coset Kb. So therefore, if this is true, then Ka is equal to Kb. Therefore, H is injective. So now we know H is both injective and surjective, therefore it is bijective. The remaining thing we need to show is that H is a homomorphism. Now H is a homomorphism. So to show that, H Ka times Kb, by the definition of multiplication between cosets, we have Kab. But by the definition of H, we have f of Ab. But f is a homomorphism, therefore we have f of A times f of B. Then by the definition of H, f of A is equal to H of Ka, and f of B is equal to H of Kb. So H of Ka times, this is Kb. Kb is equal to H of Ka times H of Kb. Therefore, H is a homomorphism. So we have seen that H is a homomorphism, it is injective, it is surjective, and it is well defined. So therefore, after all, H is an isomorphism. And we are done. In the first isomorphism theorem, we have assumed that the homomorphism between G and H, this F, is an epimorphism. But what if it is not epimorphism or anything? So suppose we have two groups, G and H, and homomorphism, which may not be epimorphism. Then what can we say? Okay, in this case, f of G is a subgroup of H, as we have seen before. So image of a homomorphism is a subgroup. Then, so in that case, then we can limit the codomain of f to the image of f. So we can have G to f of G, which is an epimorphism, right? Because it's an image. So by definition, for every element in this image, there is a corresponding element in G, such that f of that element becomes the given element. Okay. Then, based on this limitation, so this is a limited f, then so let's call this image of f. Then we can define the kernel of f, G over kernel of f, and from here to here there is an isomorphism. So that means the image of f is isomorphic to the quotient group of G by the kernel of f. Next, consider the case where we have an epimorphism between G and H, and G and H are finite groups. In this case, we can show that the order of H divides the order of G. In fact, the order of G is equal to, according to the Lagrange theorem, it's the product of the order of kernel of f and the index of kernel of f. So G index of kernel. But this index of kernel is equal to, as we have seen before, the order of the quotient group by the kernel. But since this is isomorphic to H, according to the first isomorphism theorem, that means the order of G over kernel of F is equal to the order of H. Okay, so this is equal to this because they are isomorphic to each other. Therefore, the number of elements of G is a multiple of the number of elements of H. So this is a very strong result. So just because there is an isomorphism, epimorphism here, we can show that so this is G is a multiple of H in some sense. Next, consider the case where H is a subgroup of the center of some group G. And also, suppose G over H is a cyclic group. So that means there is a generating element, HA, where all the elements of G over H is of this form, where n is an integer. However, by the definition of multiplication between cosets, HA to the power of n is equal to HA to the power of n. So after all, G over H can be expressed as HA to the power of n, where n is an integer. Okay, so each element of G over H is a coset of this form. So that means every element, let's say x and y, any element of G can be expressed as a product between an element of H and a power of A. So x is h1 times a to the power of n, and y is h2 to the power of m, where n and m are integers. Okay, because of the coset decomposition, so all the elements of G are partitioned into one of the cosets of this form. Okay, so that's why we can express this way. Now, if this is the case, then we can say that the group G is actually abelian. So to see this, multiply x and y, then that is h1 an, h2 a m. However, remember, H is a subgroup of the center of the group G. So that means any element of H can commute with any elements of G. So let's commute this. We have H1, H2, A, N, A, M. Okay. And of course, H1 and H2 can commute. A, N plus M. And H2 and let's okay, H to the power of M and H to the power of N can they commute, of course. So let's swap these, and AM H1 AN. Now this is equal to Y. This part is Y and this part is X. So any pair of elements X and Y commute. Therefore, G is abelian. So, there's nothing that says G is abelian from these conditions, but just because we happen to have these conditions, so there is a subgroup of the center of the group, and this quotient group is a cyclic group. Just because of these conditions, we can conclude that G is abelian. The next theorem is called the second isomorphism theorem. Okay, again, G is a group, and H and N are subgroups of G. And in addition, N is supposed to be a normal subgroup. In G, then we have the following isomorphism. NH over N is isomorphic to H over N cap H. Okay, so that's the theorem. And since N is normal, so NH is a subgroup of G. And N cap H is a normal subgroup of G. So there are many subgroups involved in this theorem, and the relationship between these groups are the following. So first we have the group G, into which the subgroup NH is embedded. So this curved arrow indicates that NH is a subgroup of G. Okay, and there exists a mapping, injection here. So this homomorphism indicates an injection. And we have N. So this is again injection. And H is again an injection here into NH. And N cap H is embedded in both H and N, and into which we have a trivial subgroup. Again, this is an embedding. Okay, so we have this relation between different subgroups. So let's prove this theorem. First of all, we define a homomorphism from H to the quotient group of NH by N. Yes. So we define this homomorphism by this for each element of H. P of H is defined as NH. Okay, so every element of this set is a coset like this. So clearly this mapping P is a surjection, because every element like this, so every element of this has this form. So for each of these we have H in this set H, capital H. So this is a surjection. And this is also a homomorphism, because if we map P of H1, H2, where H1 and H2 are elements of this subgroup H, then by the definition, this is N times h1, h2. And by the definition of multiplication between cosets, this is equal to nh1 times nh2, but this is equal to p of h1 and times p of h2. Therefore, p is a homomorphism. And together, surjection and homomorphism, surjective homomorphism means p is an epimorphism. So we have H and epimorphism nh over n. Then if we define the kernel of P as K, then we have another epimorphism to H over K. Then by the first isomorphism theorem, there is an isomorphism from H over K to NH over N. Okay. So this is the result of the first isomorphism theorem. So H over K is isomorphic to NH over N. Now, if we can show that K is equal to N cap H, then we are done. So this one. So if we can show that this is actually equal to the kernel of P, then we are done. So let's show this. Okay, so let's pick an element from N cap H. Then of course H is an element of N. So that means NH is equal to N, because H is an element of N, so this coset is equal to N itself. And this means, since this is the identity element of this quotient group, then that means H is an element of K. Okay, so if we pick an element from here, then it is an element of the kernel. So this means N cap H is a subset of K. Okay. Then next, let K be any element from the kernel. Then, since this is an element of the kernel, that means it belongs to so nk is equal to n, because n is the identity element of this set. So anything that belongs to the kernel maps to this element. Okay, so P K is mapped to nk by the definition of P, but since K is an element of the kernel, that must be equal to n itself. Okay. So therefore we have K belongs to n. So that means, okay, K is an element of K. And of course, kernel is a, okay, So kernel of P is a subgroup of H. So K also belongs to H. Therefore, K belongs to the intersection of N and H. Therefore, the kernel is a subgroup, a subset of N cap H. So together with this implies that the kernel is equal to the intersection between N and H. So we are done. Now let's define one term. Any non-trivial group so that contains more than one element. Non-trivial group which has no proper normal subgroup. It's said to be simple. Let's consider an example. Suppose G is non-trivial and simple and abelian group. Okay, but if G has any subgroup, then all of them must be normal because it's abelian. So every element commutes with any other element. So any subgroup will be a normal subgroup. But we are saying it's a simple group. That means there are no proper normal subgroups in this group G by assumption. So that means, but any subgroup can be is a normal group in an abelian group. So therefore, this implies that G has no subgroups, no proper subgroups. By the way, proper subgroup means that is not the group this, subgroup this, or G itself. Okay, so any other group than these are called proper subgroups. So G has no proper subgroups because of these assumptions. Okay, now let A be an element of G, and which is not equal to the identity element. Then A generates a subgroup, a cyclic subgroup. Okay, it's a non-trivial cyclic subgroup, but since there are no proper subgroups in G, so this must be equal to G itself. Okay, now if G is infinite group, is an infinite group, then A squared generates a proper subgroup. A proper subgroup, which is a contradiction. So this means we have a set like this, and this can make a proper subgroup because this does not include A itself, so it is a proper subgroup, but such subgroup cannot exist according to our assumption. It's simple and abelian. That means G must be a finite group. So this is a contradiction. Now let P be a prime number such that P divides the order of G. Then if that's the case, then P must be the order of a subgroup of G. But since there are no proper subgroups of G, so P must be equal to G itself, the order of G. So this means, so all of these, if we summarize, G is a finite subgroup, finite group of prime order. So it's interesting, just by assuming that G is non-trivial simple abelian group, we can conclude that G is finite group of prime order. And that's all for today.